Now moving on to the second part of the lecture. So this is an introduction to numerical computing. Okay, so there's going to be two parts to this. The first part, I'm going to talk about analytical versus numerical solutions. Okay, so as an engineer, we do math. This is one of the tools in our toolkit. Math is the language of nature, and we need math to be able to not only understand nature, but to be able to design useful things, useful engineering systems. Okay, so as engineers, we do math. Okay, and there are a lot of problems that we can do that we can solve by hand. So lots to do by hand. All right. So for example, here's a problem that you have almost certainly solved before, at least I hope, of a nonlinear algebraic equation. So I have 3x squared plus 4x minus 1 is equal to 0. Okay, so this is a nonlinear algebraic equation. Okay, we'll talk a little bit about that in a second. And specifically, hopefully you remember this as a quadratic equation. Right? And we can solve this by the quadratic formula. So you remember x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Right? Where this is a right here, this is b right here, and this is c right there. So that's minus 4 plus or minus the square root of 4 squared minus 4 times 3 times negative 1 divided by 2 times a, which is 2 times 3. Okay, and if you simplify that down, let's see, you get minus, let's see, 4 divided by 2 is 2, so you get 2 divided by 3 out front, plus or minus the square root. There's a 4 and a 4, so that's going to factor out actually, and we'll get a 2 out front. That 2 and a 2 cancel. So we should get 1 minus, I guess we should have another third out here, so let me back that up. So we should have another third and a square root of 1 minus, that 4 came out, so we have 3 times negative 1. So let's see, 3 times negative 1 is 3. Is that right? This seems like I made a mistake. Feeling like I made a mistake here. Let's see, 4 squared, that's 16. 16 minus 4 times 3 is 12, which would give me plus 12, right? Plus 12, that gives me 28, which is 4 times 7. So when I pull out a 4, I should have a 7 in here. So what did I miss? I pulled out, 4 squared. I should have a 4 there. Boom, that's it. Okay, so minus 2 thirds plus or minus the square root of 7 over root 7 over 3. Okay, so quadratic formula. Apologize for my little math misstep. Okay, so that one we can do by hand. But suppose I gave you this problem. Suppose instead of this quadratic formula, I said 3x squared plus 4x minus 1 is equal to 4 log base 10 of x plus 3. Okay, so this would be example number 2. Okay, what do you do now? Okay, this is still a nonlinear algebraic equation. Okay, it's not a quadratic equation anymore, and in fact, this is kind of a total mess, right? Because over here, I could try and use the quadratic formula, but I've got an x buried in here, so there's no way to isolate the x. Okay? Sometimes these types of equations are called implicit. Okay? Because that's kind of what it means to be implicit, that I can't isolate the x. All right? So we're going to learn about how to solve these kinds of equations. All right? And I actually have an example of this code. So here is this example that I'm going to show you. So I'll show you here that I have a value here of a function that looks similar to what I just showed you, 3 times x squared plus 4x minus 1. Don't worry if this code means nothing to you. It'll mean something to you in a couple of days, okay? This is my 4 times log base 10 x plus 3, all right? And it turns out that I can run this code here, and I can find what these solutions are, and I can find the answers, okay? It turns out that there's 2 different solutions, just like there were 2 solutions in this case, plus or minus, right? And we can find these 2 solutions as 0.5636 and negative 1.6436. Okay, so there were 2 solutions. Okay, but we couldn't do it by hand, right? So we could not do this by hand. All right. So we want to point out, we want to be able to distinguish between these 2 cases. We want to be able to distinguish between the case on the one hand where we can do something by hand, on the other hand where we have to do something on a computer. Okay. So we will call by hand, if we can solve it by hand, we will call that an analytical solution. Okay. On the other hand, if we cannot do it by hand, if we need a computer, okay, so I'll put need computer, we'll call this a numerical solution. Okay. All right. So now, in general, we prefer analytical solutions. So in general, analytical, okay, are better, and numerical is like really messy handwriting. Let me back up and be a little cleaner. Numerical, okay, are like only so happy. All right. So analytical are better, but this class we will focus entirely on numerical solutions. So these are actually still pretty good, okay? These are like really, really happy, okay? These are like only 1 happy face, whereas these get us 3 happy faces, okay, to have an analytical solution. And maybe we'll see why that is later, but you could maybe get a little bit of an idea from what I just showed you. So here we can write down on a piece of paper, and look, I can write down something exactly. I know that this is minus 2/3 plus or minus root 7 over 3. In this case, I don't know what if there was a radical or anything. I can't tell you. I can't tell you in terms of log base 10 of 16, or the square root of 2, or whatever. I don't have that. I just have decimal point numbers. So oftentimes numerical solutions, they have finite precision, okay, where analytical solutions can have infinite precision. Okay. Another reason that we might prefer this is it was really fast to do this. Okay, you can memorize this formula, hopefully you have, and you can write down this answer. This one, it might take the computer a while to compute it. Okay, so these are usually, you know, cheap. Okay, quick. We'll talk about what cheap means. Okay, and these ones could be more costly. Okay, big computers maybe. My face is covering that up, sorry about that. Big computers. Okay, so numerical solutions, at least in a numerical solution, at least we get one. Okay. All right, it's a big deal to have a solution rather than no solution. All right, and maybe we need to be a little bit careful sometimes about costly or finite precision, but it's better to have some solution than no solution. Okay. All right. So that's the difference between analytical and numerical solutions. Just want to point that out. Let's talk about the last part here, part B, which is classifying math problems. Okay. So to be able to solve a math problem, you have to be able to tell what kind of problem it is. Maybe that sounds like a tautology or something that's trivially obvious, but it's not. Okay. So to solve a problem, you first need to classify it. Okay. So there are many problems that we're going to be able to write that'll have this general form. So okay, so the general form will look something like f1, so our equation 1 will depend on these variables x1, x2, x3, okay, equals 0. f2 will have x1, x2, etc. And let me put xn at the end down here. So we have xn equals 0, and maybe we'll have n equations, or m equations here, x1, x2, xn equals 0, m equations and n unknowns. All right, so this is maybe our general form of many of the equations we'll have. Okay, and let's talk about classification of different things. So the first thing we'll say is if n equals m equals 1, okay, then we have a single equation. Okay, so I would just have f of x equals 0. Okay, that's just a single equation. If, on the other hand, n is greater than 1 and m is greater than 1, okay, I'm going to have a system of equations. Okay, so our first distinction, thing 1 is single equation versus system of equations. All right, so I did a system here, but it could just be a single equation if I don't have all these others. Okay, so that's thing A in terms of our classification. Okay, thing 2, all right, has to do with independent versus coupled. Okay, so if I have f1 of x1 equals 0, f2 of x2 equals 0, to fn of xn equals 0, all right, then these are called independent. Okay, or sometimes we say uncoupled, right? So really, if I just covered it up, right, if I just said, there was nothing there, I have a single equation, that's fine. But notice that if I covered that one up and all those up, then I just have a single equation there too, and it doesn't depend on anybody else. So they're completely uncoupled. Whereas if I had a situation that looked like this, where I have f1 of x1 comma x2 equals 0, and f2 of x1, x2 equals 0. If I get rid of this equation, I still have two unknowns and only one equation, okay? So that doesn't help me. Oh, lost my 0, okay? So these are not independent, okay? They're dependent. That's the right word I'm looking for. Instead of a double negative, dependent, okay? Or coupled, okay? So just think of an example. Maybe that will help really quick to see the difference here. Okay, so just of these two principles, let's just put in a quick example. So suppose I had x plus y equals 3 and x squared plus y squared equals 7. All right, so what would this be? Well, this is clearly a system because I have two equations, 1, 2. All right, so I don't just have one equation, I have n greater than 1 and m greater than 1. So n is the number of variables, right? So n is equal to 2. M is also equal to 2. I have two equations here, all right? And are they independent or are they dependent? Or are they uncoupled or are they coupled? Well, these are coupled, okay? Because I have an x and a y in both equations. So they're totally coupled together, all right? Now I could rewrite this in this form with minus 0 if I wanted. I didn't do the very good job of that, but I could say x plus y minus 3 is equal to 0, and x squared plus y squared minus 7 is equal to 0. And now that one is f1, and that's f2. All right, do you see that? So let's look at another quick example. Example 2 over here. Okay, now suppose I have x is equal to 3 and y squared plus y minus 7 equals 0, right? So what's going on here? Now this is a system again, okay? Because I have two equations. I have n equals 2 and m equals 2, but they're uncoupled. Why are they uncoupled? Well, look, I solve for x. I already have solved for x, and I can solve for y, right? I have y squared plus y minus 7 equals 0. You know, this is a quadratic equation. I can solve that just as if it was independent, okay? Just as if it was just a single equation, all right? So that's case 1 and case 2, okay? So case 1, this was single versus system. Okay, case 2 is independent versus coupled. All right, let's move on with our taxonomy here. Let's classify some more. Okay, case 3 will be, ooh, bad circle. Case 3 will be linear versus nonlinear. All right, so if I have the form, if all f's have the form f1 is equal to a11 x1 plus a12 x2 plus etc. all the way down to a1 and xn, all right, then I'm linear. Okay, so notice what I have here are constant coefficients, okay, and no powers. Okay, there's actually a more general way of defining something as linear. Maybe you learn, you know, something like if h of, I think it's something like h of ax plus by is equal to ah of x plus bh of y. Right? You probably also, this is the more formal mathematical way of defining this, but for algebraic equations, at least it reduces to this, and we'll talk about differential equations at the very end of the course. It's a little different, but if there are constant coefficients and there are no powers and there are no products, okay, then you have something that's linear. All other cases are nonlinear. Okay, there's kind of this misconception. A mathematics professor that I knew at Santa Barbara, I think, said this really nicely. There's this confusion that there's sort of this world, okay, and we divide it down the middle, and we call this one linear, and this one nonlinear. Okay, and that's really a misconception. So this is a bad idea. Okay, don't think of it this way, right? The world really is like this. Here is the world, okay, and this is linear here, okay. Okay, and these are all the things that are not linear. Okay, so it's kind of like saying there's the world and there are things that are blue, and then there's everything else in the world that is not blue. All right, and it turns out linear often means solvable by hand. Okay, not exclusively. Mathematicians hate that if you say that, but it's kind of true. Okay, what we learn in all of your classes are like, hey, things that are linear, things that obey this property up here, things that look like this, they are things that you can solve by hand. Okay, when it's not linear, it starts to get pretty hard to solve it by hand. All right, that's where we're going to come in. Okay, in numerical methods. All right, in numerical tools. That's what we're going to use. Okay, so finally, okay, so that's linear versus nonlinear. So last thing, so we're going to talk about algebraic versus differential. Okay, and if I have equations, if I replace some of the x's, so instead of if I have f of x1, x2, and now I have dx1, dx2 equals 0. Okay, now there's a differential here. Okay, this becomes a differential equation. Okay, if there are no differentials, all right, no differentials. Okay, in our class at least, that's going to be an algebraic equation. Okay, there, of course, in class of equations, there are other kinds, right? So, for example, there are integral equations. So, I'll put that there are others. Okay, you can have f of x1, x2, and then an integral of some function, another one, of x1, dx2. You could have something like this, okay? You could even have, so this would be an integral equation. Okay, they even have things like integral differential equations. So you could have f x1, x2, dx1, dx2, and some more integrals. Okay, shudder at the thought. All right, so integral differential. Okay, we're not going to worry about these two in this class. Don't worry about that. Okay, we're going to talk about these two. Algebraic equations. So these are like x squared minus 2x plus 1 equals 0. Okay, algebraic equations, differential equations. An example of a differential equation might be the second derivative of y with respect to t is, say, minus g. All right, the gravitational constant. There would be a differential equation. All right, so that's the difference between algebraic equations. Okay, so I think if you are sitting here doing this, maybe you're a little bit bored, hopefully not too much, but I'd like you to take a quick second and try an example. See if you can categorize them. So let's take our first one that we did way up at the top, 3x squared plus 4x minus 1 is equal to 4 log base 10 of x plus 3. All right, suppose we have this, label it. Let's label it according to these 4 categories here. So is it single equation or system, independent or coupled? Is it linear or nonlinear? And is it algebraic or differential? Okay, pause the video and answer that for yourself. Okay, so hopefully you paused it and answered it for yourself. Let's look at what it is. Okay, the first one, single versus system, it's clearly a single equation. All right, it's not a system of equation, it's just one equation. Okay, second one, is it linear, or let's see, second we had, is it coupled or uncoupled? Well, that doesn't make any sense because it's not a system. Okay, so can't do that. That one's only for a system. Okay, number 3, is it linear or nonlinear? It's nonlinear. How can we tell that it's nonlinear? Well, it's got a squared on the x. I have x inside a log inside this transcendental term, so definitely nonlinear. Okay, and then the last one, is it algebraic or differential? I don't see any differentials, so it's going to be an algebraic equation. All right, let's try another quick example. See if you can get this one. Okay, I'll write it down. 3x plus 2y is equal to 7 minus 4x plus y is equal to minus 2. Okay, pause the video and see if you can answer 1, 2, 3, and 4. All right, so 1, 2, 3, and 4 here. Hopefully you answered this. So is this a single or a single equation or a system? It's a system. Okay, there's 2 equations, 2 unknowns. What about coupled or uncoupled? It's coupled, okay, because I've got x's and y's in both cases, so it's coupled. 3, is it linear or nonlinear? As I look through here, I see no squares, I see constant coefficients. As a matter of fact, it looks just like this form here, constants times the values of the variables. Okay, so this is linear. Okay, and then the last case is this algebraic or differential. It's got no differentials in it, so it's algebraic. All right, last case, let's do one more example. Example 3. Okay, try this one. This is dx dt is, plus x is equal to 1. dy dt minus y is equal to 4. Okay, let's talk about these. So pause it, see if you can figure this one out, and then I'll answer it. Okay, so I have these guys. What am I, a system or am I a single equation? I'm a system. Okay, because I have 2 equations. But I only have x's here and I only have y's here, so this is uncoupled. All right, for number 3, is it linear or is it nonlinear? Well, I see no powers, no products. Okay, I don't have x times dx dt. That would make it nonlinear. Okay, I just have a dx dt, so this is linear case. Okay, this is linear differential equation. All right, and finally, is it oh yeah, that's linear. And is it differential or algebraic? It's clearly differential. Okay, so that's the little example that we have for you. All right, this is very similar to what you're going to be looking at on your homework. Hopefully that makes sense to you. That's all I have for you in this lecture, and I hope you have a great one.